Hello everyone, my name is KNS Swami. In this session, I am going to explain electromotive force. So this is the important part in electrochemistry chapter. So in this particular session, I am going to explain electromotive force, what is electromotive force and what is cell potential. So what is electrode potential and what is the relationship between Gibbs free energy and this electrode potential. Okay, so after that we are going to solve some of the questions related to this EMF or electromotive force. Okay, now let us start this session. Now let us see what is electromotive force or EMF of the cell. So here this is the statement. So it is defined as the maximum potential difference between the electrodes when the cell is not in use. Okay, so here the maximum potential. So here the maximum potential difference between the electrodes when the cell is in not use. Okay, so here what is the meaning of this statement? Okay, so here I am considering there is a circuit that is here. This is the battery. So this is my battery. So this is the positive terminal and negative terminal. So here I am connecting this battery. So I am connecting this battery to the bulb. So okay, so now this battery contains, let us assume 5 volts of potential. Okay, so initially it will be having the potential that is 5 volts. Okay, now if it is open circuit, so these all connections are not made in contact with each other and it is a open circuit. Okay, so at that case, there is no passage of current to this into this circuit. So in this circuit, okay. So if I connect this battery to the bulb through a switch, and it is if it is closed circuit, so it is closed circuit now. So there is a passage of current positive terminal to the negative terminal. Okay, so in this direction. Okay, so after some time, if you observe the voltage of this battery, so it will become 4 volts. After some time, so it will become 3 volts. So it means by increasing the time, so by time increases, so the voltage of the battery will be decreases. Is it right? So here, if there is increase in the time, so there is a decrease in the voltage in the battery. Okay, so at time t is equal to 0, you can observe the voltage 5 volts. At time t is equal to 10 seconds. So after 10 seconds, you can be observe the voltage that is 4 volts. After time t is equal to 15 seconds, so you can observe 3 volts. So it means with increasing the time, so there is a decrease in voltage of the battery. Okay, now here the maximum potential difference that is observed at the time t is equal to 0. So this voltage, what we call as EMF of the cell. So EMF of this particular cell. Okay, it means here, so the maximum potential difference between the electrodes. So when the cell is not in use, so there is no current drawn from the cell. So at time t is equal to 0, so there is no current drawn from the cell. So here, so this 5 volts, so this is the EMF of the cell. Okay, now for better understanding, so I am assuming a galvanic cell. So before going to that, so here I am taking a beaker which is containing a metal ion solution. So metal ion solution. Okay. So here we have metal ions with the Mn plus charge. So where M is the metal, N plus is the valency of that metal. Now if I place the metal rod, so if I place the metal rod, so which is a same metal which is present in the which is present in the solution. Okay. So here when this metal rod in contact with the metal ion solution, what happens? Atoms, the metal atoms that are present on the metal, they are trying to move into the solution. So they are trying to discharge into the solution. And the metal ions which are present in the solution, so they are trying to deposit on the metal surface. So by accepting electrons. So here there are two phenomena takes place. So one is the metal atoms that are present on the surface of the metal. So they will try to came into the solution. So by losing electrons. So it means, so this metal will lose the electrons and it will converted into ion. So they will get into the solution. Okay, so here it is a solid metal, so which is came into the aquatic solution. So this process what we call as so oxidation process. So from zero oxidations to N plus, so there is an increase in oxidation number. So increase in oxidation number what we call as so oxidation process. So this is oxidation. This is oxidation. Okay, so this is oxidation. Okay, so due to the discharge of the metals from surface of the metal to the solution, so there is a increase in negative charge density on the metal and there is a increase in positive charge density in the solution. So here there is a charge separation between this metal rod and this metal ion solution. So due to this charge separation, so there is the existence of some potential. So that potential, what we call as electrode potential. So that is electrode potential. Electrode potential. Okay, so here the potential difference between metal rod and metal ion solution, what we call as electrode potential. Okay, so this potential is due to the charge separation between the metal rod and electrolyte solution. Okay, so here I am considering oxidation reaction. So due to oxidation reaction, so there is a deposition of, there is a discharge of metal ions from the metal surface and there is an increase in electron density on the metal. So this potential, what we call as oxidation potential, oxidation potential, oxidation potential. Okay, so electrode potential can be represented with the help of the symbol capital E, and the oxidation potential can be represented as E oxidation. E oxidation. So this oxidation will takes place at anode. So it is also represented as the potential at the anode, the potential at the anode. Okay, so now let us assume another beaker which is containing a metal ion solution, which is containing a metal ion solution. So here metal rod dipped in a metal ion solution. So here this is our metal ion and this is metal ion solution. Okay, so here in this case, if the metal ions will try to deposit on the surface of the metal. So here these metal ions will try to deposit on the metal surface. It means this Mn plus is accepting electrons. So is accepting electrons and it will converted into metal. So which is a solid metal. So the ions which are present in the aquatic medium, so they are move on to the surface of the metal. Okay, So this is a reduction process because here there is a decrease in oxidation number. So it is a reduction reaction. So due to this reduction reaction, so we can observe reduction potential, reduction potential, reduction potential, reduction potential. Okay. So here, so it can be represented as E reduction. So this reduction will takes place at cathode. So it is cathodic potential, E cathode. So here, so oxidation potential means, so due to oxidation, the potential will develop at the electrode electrolyte interface. Due to reduction, the potential will be developed at electrode electrolyte interface. That potential what we call as reduction potential. So here, so due to oxidation as well as reduction, there is a potential developed at electrode electrolyte interface. Okay, now here, if I measure this electrode potential at the standard state, that means at pressure 1 bar, at pressure 1 bar and temperature 25 degrees centigrade, and the concentration of the solution is 1 mole. If the metal ion concentration, metal ion solution concentration is 1 mole, that potential is what we call as standard electrode potential. Standard electrode potential. Standard electrode potential. Okay. So this is the standard electrode potential. So when the electrode potential is measured at the standard condition. Okay. Now let us see here. The electrode potential is it is defined as the potential difference between the rod and electrolyte solution. Okay. So let us assume a cell, that is galvanic cell. So here this is my electrolyte solution. So let us consider it is A. So this A will converted into A plus is converted into A, and this B plus is converted into B. Okay. So this is the metal rod. So here this is another container which is containing electrolyte and electrode. Okay. So here these are connected through a. Okay, so this cell will be having some potential. Let us say it is having small potential. Okay, so it will be having high potential. Okay, so now if this is the situation, so if I connect these two half cells, so there is no passage of electrical current. So that is there is no flow of current. So if I place the salt bridge, if I place the salt bridge, so this is the salt bridge. This is the salt bridge. So if I place this salt bridge, so the current will flow from highest potential to the lowest potential. So it means current will flow from this highest potential to the lowest potential. Okay. So now what is the EMF of this cell? So initially, before placing the salt bridge, so suppose it may contain the potential that is 10 volts. So if after connecting this salt bridge, that means after t is equal to 10 seconds. So t is equal to 10 seconds. At t is equal to 0, we have 10 volts. And at t is equal to 10 seconds, so you can be observed the potential of this cell will be decreases. So it will become 8 volts maybe. So the at time t is equal to 20 seconds, so it will become 4 volts. Okay. So here, so there is a decrease in potential with time. Okay, so here, what exactly the EMF of the cell? So here the EMF of the cell is 10 volts. So because the maximum potential difference between these two electrodes at time t is equal to 0, that means that cell is not in use. So this 10 volts is the EMF of the cell. So this remaining this 8 volts and 4 volts. So what we call as cell voltage. Cell voltage. Okay, so this cell will be having this half cell will be having highest potential, which is act as a cathode, and this half cell will be having smallest potential, so it will be act as a anode. It will be act as a anode. Now, what is the EMF of this cell? How to calculate this EMF of this cell? So the EMF of the cell, that is E cell, so can be calculated as the potential of the highest electrode, the highest potential electrode minus lowest potential electrode. That means the potential of the cathode, so which is having highest electrode potential, minus so the potential of the anode. Okay, so here the E cell of a particular electrochemical cell can be defined as the difference in the electrode potentials, the potential difference, the maximum potential difference between the electrodes in a cell when they are not in use. Okay, so the maximum potential difference between two half cells, what we call as E cell. Okay, that can be calculated as E cell is equal to potential of the cathode minus potential of the anode. Okay, okay. So let us see here. So generally, this electrode potential will be represented as reduction potential. So here, so for example, so it will be having reduction potential, that is A plus by A is equal to 2.0 volts. Let us assume. Okay, so this half cell will be having, so B plus B is gives rise to 3.1 volts. Now, what is the EMF of the cell? So here both are reduction potential. Okay, so the half cell which is having highest reduction potential, that will be tendency to undergo reduction, that will be act as a cathode. So it will be act as a cathode, and it will be act as a anode, that is lowest reduction potential. Okay, so now the EMF of the cell, as we know that, so the potential at the cathode minus potential at the anode. So you can simply calculate. So 3.1 minus 2.0, which is a 1.1 volts. Okay, so the EMF of this cell is 1.1 volts. Okay, so in this way, you can calculate the EMF of the cell. Okay, now let us assume the standard electrode potential. That means again, so if they are given standard reduction potential, so that is SRP, standard reduction potential. So standard reduction potential means every cell will be having some standard reduction potential. So that is measured at the 25 degrees centigrade temperature, and the concentration of that electrolyte solution is 1 molar, and that will be measured at the pressure 1 bar. And every element, so they can contain some standard electrode potential, so that will be observed as a electrochemical series. So here the every metal, that is every element, will have some potential, electrode potential. So that electrode potential will be measured at the standard state. So that standard state potential, what we call as standard reduction potential of that particular element. Okay, so that will be measured with the help of standard electrode, that is standard hydrogen electrode, which is having electrode potential 0. Okay, so here let us consider this galvanic cell. Okay, so in this galvanic cell, So zinc rod dipped in a zinc sulfate solution. So this zinc will undergo oxidation. So here, so this zinc will undergo oxidation. It means zinc is gives rise to Zn plus 2 electrons. Okay, so it is oxidation reaction. And this copper, so which is copper rod dipped in a copper sulfate solution. So this copper will undergo reduction by accepting 2 electrons. So copper will deposited on the surface of this metal, and zinc will discharge, zinc atoms discharge from the surface of the metal to the solution, and there is an increase in electron density on the surface of the metal, and there is an increase in concentration of this zinc sulfate solution. So increase in concentration of Zn plus 2 ions. So as a resultant, so there is oxidation takes place. So it will be act as a anode. It will be act as an anode. So here, so the reduction takes place. It will be act as a cathode. Okay, so here electrons will flow from this anode to cathode, and the direction of electrons is from anode to cathode, and the current will flow from, so cathode to anode. So this current will flow from cathode to anode. Okay, so this is a simple galvanic cell. Now let us see what is the relationship between this electrode potential and uh, free energy, that is Gibbs free energy cell. So what will be the relationship between the EMF of the cell and the Gibbs free energy? Okay, so here I am simply writing the expression which is represents the relationship between the EMF of the cell and the Gibbs free energy. So that relation is delta G is equal to minus NF E cell. Delta G is equal to minus NF E cell, where delta G is the Gibbs free energy change in a particular electrochemical reaction. So you know the significance of this delta G as you have studied in thermodynamics. Okay, so where N is equal to, so where N is the number of moles of electrons transferred from anode to cathode. So here electrons will flow from anode to cathode, and current will flow from cathode to anode. So F means Faraday's constant, which is 96,500 coulombs, which is having the value. So here E cell, that is electrode potential. So electrode potential. So if I take a standard electrode potential, so our standard free energy change, that is delta G naught is equal to minus NF E naught cell. So this is the standard free energy change, the standard free energy change. Okay, now what will be the relationship between this delta G, that is change in free energy, and E cell, that is E naught of this electrode potential of this cell? Okay, now let us see here. So if delta G is equal to the 0, what happened? If delta G is equal to the positive, what will be what happened in the electrochemical cell? And delta G is negative, what happened here? Okay, so now let us see, if delta G is negative, it means the change in free energy of that electrochemical reaction is negative. At that case, that reaction will take place spontaneously. So that reaction will take place spontaneously. For spontaneous reactions, delta G will be negative. And if the delta G is negative, so from this expression, the E cell of this electrochemical cell will be positive. Am I right? So there is a working, there is a current flow in the electrochemical cell, so that will produce some potential that is having some value, that is positive value. So here, so if the delta G is negative, so that will be having E cell that is positive. Okay, so if the delta G is positive, if the delta G is positive, that reaction will take place non-spontaneous, non-spontaneous. So non-spontaneous reaction. Okay, so if the reaction is non-spontaneous, so cell will not working its own. So it will be having E cell that is a negative, negative E cell. So here, so the cell potential will be negative. So if delta G is equal to 0, so there is no change in the reaction. So that means there is no change in the free energy of that reaction. So it means, so that cell is in at equilibrium. Cell reaction will be in equilibrium. So at that case, E cell will become 0. So there is no flow of current will takes place. So there is no cell potential. So that is E cell will be 0. Okay. So here, so if the delta G is equal to 0, so cell potential will become 0. There is no flow of current will takes place. And if the delta G is positive, so that reaction will takes place non-spontaneously. So at that case, the cell potential will be negative. Okay, so here, if the change in free energy, change in Gibbs free energy is negative, that reaction will take place spontaneously. Okay, so at that case, so the E cell of that particular cell, electrochemical cell, is positive. Okay, so this is the relationship between so cell potential, that is E cell, and the change in free energy of that particular electrochemical reaction. Okay, so this is about the, so what is electrode potential and what is EMF of this cell, that is electrode electromotive force, and what is the relationship between change in Gibbs free energy and EMF of the cell. Now let us try to solve the some of the questions related to this EMF of the cell, that is electromotive force. So here there is a question. So they given that the standard potential, that is E naught of Cu plus 2 by Cu and Cu plus by Cu are 0.34 volts and 0.522 volts respectively. The E naught of Cu plus 2 by Cu is. So if you see this question, so they have given the standard reduction potential, that is, so E naught of Cu plus 2 by Cu is 0.34 volts. Okay, so and also they have given so the standard reduction potential of Cu plus by Cu. So here it is reduction potential. Why I am calling this reduction potential? So here copper plus 2 is converting into the copper atom. So this notation denotes the copper plus 2 is converting into the copper. So it means there is a decrease in oxidation number. So decrease in oxidation number, what we call as reduction. So this potential, what we call as reduction potential, that is standard reduction potential. That is for this, we have 0.34 volts, and copper plus by copper is 0.522 volts. Okay, now if I write this reduction reaction, that is copper plus 2 to copper. So here copper plus 2 will take 2 electrons and it will convert it into copper. And the free energy of this reaction, that is delta G1. Let us assume this is a delta G1. The Gibbs free energy change is delta G1 for this reaction. Now this is another reduction potential, that is copper plus by copper, so which is given 0.522 volts. So here the reaction of this reduction is Cu plus electron is gives rise to Cu. Okay, so Cu. So the standard free energy change, that is standard free energy change, that is delta G naught is equal to, so delta G naught to 2. Okay. So now if they are asking the standard reduction potential of copper plus 2 to copper. So we have to calculate this one. So this will be something. So Cu plus 2 plus electron is gives rise to Cu plus. So this Cu plus. So the change in free energy is delta G3 naught. This is the change in standard free energy change. Okay, so this, if you observe this, so this reaction, that is delta G3, so this reaction will be obtained by subtracting this delta G1 and delta G2. So this is the reaction 1 and this is reaction 2. So this is reaction 3, which I got by subtracting the reaction 1 from reaction 2 from the 1. Okay, so if I subtract this reaction 2 from this reaction 1, so you will get this reaction 3. So it means the standard free energy change of this reaction is equal to the, so the standard free energy change for a first reaction, that is copper plus 2 to copper minus, so the standard free energy change, that is delta G naught to 2. Okay, that is copper plus 2 copper. Okay, so now we know that, so for this change in free energy of a cell, so that is delta G naught is equal to, so is equal to the, so minus NF E naught of the cell. So let us substitute this expression here, minus NF E naught of the cell 1, that is E naught 1, that is E naught 3, so that is delta G3 naught is equal to the, so minus NF E naught 1 minus NF E naught of this E2. Okay, so here where N is the number of moles of electrons transferred, where F is the Faraday's constant. Okay, so if I will write this expression as, E3 is equal to, so NE3 naught is equal to NE1 naught minus NE2 naught. Is it right? Is it right? So here I want to calculate this E3. So that is for this reaction. So that is copper plus 2 to copper plus. Okay. So here we know the value of E1 and E2. So we know the values of these N. So this reaction, for this reaction, the value of N is 1 because here there is a transfer of 1 mole of electron. For this E1, so there is a transfer of 2 moles of electrons. So the N value will be 2. And for this second reaction, so that is this reaction 2, there is a transfer of only 1 mole of electrons. So I will substitute this over here. So E3, 1 into E3 naught, that is E3 naught is equal to 2 into the electrode potential of this reaction is 0.34, that already given in this problem. So that is 0.34 volts minus, so N1 Ne2 naught for this second reaction. So number of electrons transferred is 1. So that here 1 into 0.522, that is 0.522 volts. Okay, so if you calculate this, so E3 naught is equal to 2 into 0.64 means 0.68 minus 0.522. So that means, so it will be around 0.158 volts. So this is the cell potential of this the standard cell potential of this copper plus 2 to copper. So that is 0.158 volts. Okay, this is a standard reduction potential. So here the correct option is 0.58 volts. So this is the correct option. Is it clear, all of you? Is it clear? So first of all, you have to study the problem. So first, they have given reduction potential for copper plus 2 to copper and the copper plus 1 to copper 0. So they are asking to calculate copper plus 2 to copper plus 1, the standard reduction potential of this reaction. So here, so first of all, you have to write the reaction, that reduction reaction for this first one and second one. And this is for you have to calculate reduction potential. So by subtracting the equation 2 from this equation 1, you will get the equation 3. So the standard gives free energy change for each reaction can be assumed as delta G1, delta G2, and delta G3. So you will get the delta G3 by subtracting the delta G1 and G2. So by subtracting delta G2 from the delta G1. So here we know that delta G naught is equal to minus NF E naught of the cell. Is it right? So where N is the number of moles of electrons and F is the Faraday's constant, that is 96,500 coulombs, which is a constant. And E naught of the cell. So already they have given E naught of the cell for a delta G1 and a delta G2. So we have to calculate E naught of the cell for delta G3 naught. So which is a E3 naught. So in this way, you can calculate the cell potential, that is standard electrode potential. So standard cell potential of a particular cell with the help of this free energy, with the help of the relationship between this electrode potential and free energy change, that is Gibbs free energy change. Is it clear, all of you? Is it clear? So shall I move on to next one? So now this is our question. So in this one, standard electrode potential of copper plus 2 to copper, they have given 0.34 volts, and the standard electrode potential for Zn plus 2 to Zn, so 0.76 volts. Here they have given reduction potential of the copper and zinc. The reduction potential of this standard reduction potential of this copper is 0.34 volts, and the standard reduction potential of this zinc is 0.76 volts. Okay, so let us calculate the EMF of this cell, the standard electrode potential for this cell. So here E naught of copper plus 2 to copper is 0.34 volts, and E naught of Zn plus 2 Zn is equal to 0 point minus 0 point, it is plus sign, it is minus sign, minus 76 volts. Okay, so here both are reduction potentials. So as we know that, so how to pick up which one is cathode and which one is anode? So the reduction potential, if the reduction potential is high, it means it will be having highest reduction potential, that will be having more tendency to lose the that will be having more tendency to get reduced. So it means it will undergo reduction reaction. Okay, so here if you observe these two values, so it is something 0.34 volts and it is minus 0.76 volts, which is greater value. Obviously this 0.34 is the greater value. So it will be act as a cathode. So here it will be undergo reduction reaction, and here it will be act as a anode. it will be act as a anode. Okay, so here, so at by calculating this E naught of the cell is equal to E naught of cathode minus E naught of anode. So that is equal to for cathode 0.34 volts minus of minus anode 0.76 volts. Okay. So by calculating this, you will get nearly 1.1 volts. Okay, I think. Okay, so E naught of this cell is 1.1 volts. Okay, so due to the redox reaction, so it will produce the cell potential, that is standard standard cell potential, that is 1.1 volt. So during this electrochemical reaction, so this copper will undergo reduction. So by take up the 2 electrons, so this copper plus 2 will undergo reduction. Okay, zinc will undergo oxidation. Zinc will undergo oxidation by losing electron. By losing 2 electrons, the 2 electrons will take up by the copper plus 2 and it will be deposited. Okay, so this is anode, this is cathode, this is cathode. So this reaction can be written as Zn plus Cu plus 2 is gives rise to Zn plus 2 plus Cu. This is the electrochemical reaction. So here in this case, so zinc will be discharged from the anode, so anodic part, and there is a deposition of copper will take place at the cathode, and there is a flow of electrons from the anode to cathode, and there is a flow of electric current, that is current will flow from cathode to anode. So current will flow from, so current will flow from cathode to anode. Okay, so at that case, so zinc will discharge, zinc will discharge at anode, and copper will deposited at cathode. Okay, so this is a case we can observe here. Okay, now if I connect, this is the spontaneous process, so without interfering any external voltage. Okay, so now if I connect this cell to the battery, so here what they have given actually. So identify the incorrect statement from the following, from the options given below. So here they have connected this cell, what we have discussed here, that will be converted into external circuit. External circuit, simply you can take as a battery. So if I connect this cell to the battery, what happened here? Now let us assume if the voltage of the battery, that means E external voltage is less than 1.1 volt. If external voltage is less than 1.1 volt, so there is a flow of current from this cell to the battery. So it may, because highest potential to current will flow from highest potential to the lowest potential, so that so current will flow from cell to the battery. Okay, so it means spontaneous reaction will be takes place. At that case, at anodic compartment, zinc will discharge, and at cathodic compartment, copper will deposited. Okay, so here, is it clear here? So here, if it is the case, so zinc will discharge and copper will deposited. So current will flow from from cell to the battery. Now let us assume another case here. So E external is greater than 1.1. So it means, so current will flow from battery to the cell. So there is a non-spontaneous reaction will take place. So here it is spontaneous. It is non-spontaneous reaction. Non-spontaneous reaction. At this case, zinc will be deposited. So zinc will deposited means it will undergo reduction. It will be act as a cathode. It will be act as a cathode. Here it is anode. Here it is cathode. Okay. So copper will discharge. Okay. It will be act as a anode. So it is the opposite reaction. So there is a reverse reaction will take place when the potential of the external circuit is greater than 1.1 volt. Okay, so this is a case where when the potential of the external circuit is, that is E external, potential of external circuit is 1.1. What happened here? So at this case, the potential of the cell and external circuit is same. There is no flow of electrons will take place. Are you getting my point? Is it clear? Is it clear, all of you? So now let us examine these options. So here, if external E external is equal to 1.1 volts, no flow of current occurs. So this statement is correct. So here they are asking incorrect statement. So this statement is correct. Okay. Now let us examine option 2. That is, if E external is greater than 1.1 volt, zinc dissolves at the zinc dissolves at zinc electrode and copper deposited at the copper electrode. So E external is greater than 1.1 volt. Zinc will, so what I am saying here, so exactly, so at this case zinc will be deposited. Okay, so they have given dissolution, so it is not correct. Okay, so if you see this option C, if E external is greater than 1.1, so electrons will flow from copper to the zinc. That means here, so electrons will flow from copper to the zinc. It means from here, a anode is copper. So from anodic compartment to the cathodic compartment, there is a transfer of electrons will take place. So again, this is correct statement. Okay. Now E external is less than 1.1 volts. So zinc will dissolve at the anode and copper will deposit at the cathode. So is it correct? So here I have discussed here. So E external is lesser than 1.1 volts. So zinc will discharge and copper will be deposited. It is a spontaneous reaction. So current will flow from cell to the battery. Is it clear? So this is also correct statement. So the incorrect statement is B. So the correct option is B. Is it correct? So so this option B is the correct option. Is it clear? Is it clear, all of you? Yes. Now, I will move on to the next one. So this question is related to organic chemistry. So now the major product in the given reaction is, so here this is my reactant and they have given H plus and heat. And in the second step, that is HBr, treatment with HBr. So here I'm writing here OH, H. Yes. Okay. So this is my substrate on treatment with H plus. So the here this oxygen will be having a lone pair of electrons. It will take up the H plus, and it gives OH2 plus. Okay. So now it will by heating. So they have given heating. So here there is a dehydration. So minus of H2O. It gives a carbocation. So it is a carbocation. It is a carbocation. Now this carbocation will undergo rearrangement. So here this carbocation will undergo rearrangement. So this is carbon number 1, 2, 3, 4, 5, and this is 6. So now, so there is a cyclization of this will takes place. So you will be expected that two kinds of cyclic products. So one is 6-membered ring, that is this one. And another one is 5-membered ring. This one. Okay. So if you observe this, so this is a secondary carbocation. So it is tertiary carbocation. So tertiary carbocation is more stable than secondary carbocation. So there is no possibility of this kind of cyclization. So which is leads to the 6-membered ring. So you will not observe this one. So here we can observe this cyclization product. So this cyclic product so will react with the HBr. So this H plus and Br minus. So this Br minus will attack over here. So you will get the product like this. So this is our product. Okay. So if you see the option number 3, that is option C. So which is our product. Okay, product. So this is our product. So the correct option. Is it clear, all of you? Shall I move on to next one? Yes. So arrange the following in increasing order of reactivity towards the nitration. So here they have given nitration. So here paraxylene, bromobenzene, mesethylene, nitrobenzene, and benzene. So this question is related to benzene and its reactivity. So nitration of benzene. So in this nitration reaction, this NO2 plus, so NO2 plus act as a electrophile. Electrophile. Okay. So this is electrophilic substitution reaction. Electrophilic substitution. Electrophilic substitution reaction. Okay, this is electrophilic substitution reaction. Okay, so here, if you observe electrophilic substitution reaction in aromatic compounds, when they are containing electron donating groups like electron ring activating groups, when the ring activating group is present, the rate of electrophilic reaction will be increases. When the ring deactivating group is present, so the rate of the rate of this electrophilic substitution will be decreases. So if you write this these compounds over here, this is my nitrobenzene, bromobenzene, benzene, and paraxylene, and this is my mesitylene. Okay, okay. So here, if you observe these, so this nitro group is a strong deactivating group, strong deactivating group, strong deactivating group than bromine. And here, if you observe this methyl group, which is a activating group, activating group. So in presence of ring activating group, the rate of electrophilic substitution reaction is more. So there is an increase in reactivity of this compound will increases when the ring activating group is present on the ring. So here we have three methyl groups. So it will be having more activating groups. It means it will participate more in it will participate in more in the electrophilic substitution. Okay, so here if the more number of ring activating groups, there is a more reactivity towards the nitration. If the less number of ring activating groups, so there is a less in the reaction. Okay, so here it will participate more in nitration reaction. The reactivity will be more for this mesitylene and then paraxylene. So here this is benzene, which is not having any activating or deactivating group. So here we have bromine and nitro group. So this Br, which is act as a deactivating group, and nitro group is also act as a deactivating group. So nitro group is a strong deactivating group, so that the rate of nitration will be decreases in this nitrobenzene, so that you can observe the order will be like this. So the nitration reaction will be more more in the mesitylene, and then this paraxylene, and then benzene and bromobenzene and nitrobenzene. So if you observe these options, so here mesitylene we have this C. So C is more, and then A is the paraxylene, and E is the benzene, and bromobenzene and nitrobenzene. So the correct option is B. Are you getting my point? Here this is only simple concept, that is ring activating groups and ring deactivating groups. So ring activating groups will increases the rate of reactivity towards the nitration reaction, that is electrophilic substitution reaction. If the ring deactivating group is present, so that will decreases the rate of reaction towards the nitration. Is it clear? This is all about today's session. So I will stop here. So thank you for watching. Have a nice day.